need to access configuration files, static assets, or any server-hosted data without writing custom HTTP handlers. We'll use FastMCP's resource system to list available files and read their contents with just 2 async calls. You'll see how the client handles file URIs, returns structured content, and integrates seamlessly with the rest of the MCP protocol. No manual parsing required. Async with client. Hash list available resources. Resources equals await client list resources. Hash read a resource. Content equals await client read resource. File //config/settings. JSON. Print content 0. Text. This demonstrates the context manager pattern combined with asynchronous resource handling. The pattern creates a controlled execution scope where connection lifecycle is managed automatically, ensuring proper initialization and cleanup without manual intervention. What makes this distinctive is how it combines async I/O with deterministic resource management, preventing connection leaks or improper state transitions. The approach works by encapsulating connection state within the context manager's enter-exit protocol. All operations become methods on the client object, with the context manager guaranteeing the client is properly connected before any operation executes and fully cleaned up afterward. This separation of connection management from business logic follows the dependency injection principle, where the context provides a ready-to-use client rather than requiring manual setup. This pattern matters because it solves the common problem of resource management in async environments. Without it, you'd need explicit connection-disconnection calls wrapped in try-finally blocks, which becomes error-prone in complex async workflows. The trade-off is slightly more boilerplate for the context manager itself, but the payoff is cleaner, safer code that's less prone to connection leaks or improper state handling. It's particularly valuable in testing scenarios, production services, or anywhere you need reliable connection management without manual oversight. Let's break it down line by line. Async with client. Async context manager pattern ensures the client connection is properly initialized and cleaned up after use, preventing resource leaks. Critical for async operations where manual cleanup would be error-prone. Hash list available resources. Resources equals await client list resources. This enumerates all available resources from the MCP server. Required first step before reading or modifying any resource, as you need to know what exists to interact with it. Hash read a resource. Content equals await client read resource. File //config/settings. JSON. This reads a resource from the MCP server using its URI path. The file // protocol specifies we're accessing a file resource. Here, config/settings, JSON, and the async call handles the I/O operation without blocking. This pattern mirrors standard file system operations, but works across MCP's unified resource interface. Print content 0. Text. This accesses the text content of the first resource returned by read resource. The array index 0 handles cases where multiple resources might match, while text extracts the raw content for printing or processing. Resource access pattern. The async context manager with FastMCP's client handles both connection lifecycle and resource operations, automatically managing server initialization while exposing resources through standardized URI schemes. Resource URIs must include the scheme prefix, like file, // or resource, //, or the client will fail silently with empty results. This pattern creates a unified interface for text, binary, and multi-server resources without changing the core interaction model.
The URI that names nothing becomes the path to everything.